So in the previous lecture we had looked at what was called the notion of gradient of a vector field for a scalar field. For a scalar field which is a function of 2 or 3 variables, we can define the notion of gradient, and that is nothing but the partial derivatives with respect to the respective variables. So for a function f, if fx, fy and fz are the partial derivatives and all of them exist at a point ABC in the domain, then we can consider the vector with components fx, fy and fz, and that is called the gradient vector and denoted by this delta f. And we proved an important property which relates gradient with directional derivative, namely if a function f is differentiable, then the directional derivative of f in any direction u can be represented as a dot product of the gradient vector with a unit vector u, that is a direction. So that is if the function is differentiable. And we gave conditions and we gave examples to illustrate that you cannot delete the condition that the function is differentiable. In that case, this may not be true. We give another interpretation of this equation, that the directional derivative is equal to dot product of two vectors. It gives a very nice interpretation, and that comes from the fact that dot product of two vectors a and b is nothing but absolute value of a into absolute value of b into the cos of the angle between them. So here the directional derivative is equal to dot product of these two vectors. So I can write this as absolute value of the gradient vector, absolute value of u, which is a unit vector, into the angle between the unit vector and the gradient vector. And we know that the cos of the angle, that is theta. Now cos theta takes values between 0 and 1, minus 1 and 1. So the minimum value of cos theta is minus 1, maximum is plus 1. So that tells you that the directional derivative in which directions will be maximum and the minimum. And what is directional derivative? That is the rate of change of the function in that direction. So written that way, this formula, this equation will give us the directions at the point ABC in which a function will increase most rapidly or decrease most rapidly, and the direction which are perpendicular, there is no change. Cos theta will be equal to pi by 2, that is 0. So those are the direction in which there is no rate of change of the function at that point. So let us write that as a theorem. So it says that consider a function f of 3 variables defined in a domain D, and such that let us assume that the gradient vector is not 0, because if a is 0, then the dot product is 0. You can't conclude anything then. So the vectors a and b should not be 0. U is a unit vector already, so we assume that the gradient vector is not 0 at the point ABC, and u is a unit vector, then the following hold. So as I said earlier, at the point ABC, the direction in which f increases most rapidly is the same as that of the gradient, because when is cos theta maximum, then theta is equal to 0. So it should be the same as u and directional derivative, u and the gradient vector should have the same direction. So in the direction of the gradient vector, the function will increase most rapidly, and similarly in the direction opposite, it will decrease most rapidly. And in the directions which are perpendicular to the gradient vector, cos theta is equal to 0, theta is equal to pi by 2, so there will be no rate of change of the function in those directions. So this is a simple and useful property of the gradient. So as I said, the proof is just look at the same equation, that the directional derivative is equal to the dot product of gradient with u, and now write a dot b is equal to absolute value of a into absolute value of b into cos theta. Now cos theta takes values, maximum value, minimum value, and the value to be 0. Accordingly you get the consequences between theta and 0 and pi. So values are between minus 1 and 1. So it is maximum when cos theta is equal to 1, and that is same as direction of maximum increase for the function at that point. At that point you are looking at in which direction you should move so that the rate of change is maximum. So that has important applications. So this is the direction of the gradient. So you want only direction, so you take the unit vector. So that is the direction in which the function will increase most rapidly. And when it is the cos theta is minus 1, then it will be the least. So that is the opposite direction is the direction in which it will be, right? increasing least, or it is the maximum decrease, you can call it if you like. And the directions perpendicular are the ones which will give you no rate of change. So a simple consequence of that same formula, and that formula, if you remember, was only true when we proved under the conditions that f is a differentiable function. So that is important to remember. So simple examples to illustrate the point. Fxy is equal to 4 minus x square minus y square. This function is differentiable everywhere, so no problem. So let us compute the partial derivatives. Fx, Fy is a function of two variables only. So the gradient vector is a vector in the plane. It has only two components. So and let us look at the point x0, y0 is 1, 1. Then this is the direction in which the function will increase more separately of that. And steepest ascent, that is, there is another word used, sophisticated, for increase, maximum increase, okay? So, and what is the value of that rate of change? That is the absolute value of the gradient vector, right? That is the maximum value of the rate of change. So this is the direction in which it will increase most rapidly at the point 1, 1. And decrease will be the opposite of that, so that will be plus minus, right? There are two possibilities, taking of the square roots. No change will be, no change is pi by 2, so up or down, right? Perpendicular to the gradient vector, so two directions are possible. And since the gradient is 0 at that point, so there will be no change at 0, 0. If you're looking at the point 0, 0 instead of 1, 1, then the gradient vector is 0 there. So in any direction, directional derivative will be 0 in that case. So there is no rate of change at any point, in any direction at that point. Similarly, just another, making it slightly, say that it is a useful result, you can call that function fxy is equal to 20 minus this, temperature of a metallic sheet now you can think of, right? So there is a surface, right? At every point you have got the temperature, and at any point you want to know in which direction the temperature is increasing most rapidly or decreasing and so on. So the basic idea is same. So let us calculate, we want to, in that, on the surface of that, on that surface, metallic sheet, we want to find a path, so that if you move along that path, you always will be having maximum rate of, temperature will be increasing maximum. What is that path along which you should move? We want to find that. And we are starting at the point 2, 1. So at the point 2, 1, we will compute the gradient vector. That is the rate of maximum increase. So at that point, in that direction, we should be moving. Okay. So let us say that the path which you should be moving, there is a curve on the surface. So call it as xti plus ytj. Xt, yt are the components of the curve on that surface along with you want to move, so that there is a maximum increase at every point. So that means what? That means the derivative on that the tangent vector at any point of the curve should be same, having the same direction as that of the gradient vector at that point on the surface, right? That is the direction of maximum increase. So at a point, if you want to move along the curve, you are moving along the tangent direction, right? In that direction. So tangent vector at any point to the curve should be same as that of, direction should be same as that of the gradient. So let us find the tangent vector, that is this, and that to be maximum, it should be equal to alpha times, or alpha times that should be equal to the gradient vector at that point. We don't know what is alpha, we will find some alpha. Okay. So write down that gradient vector, we know it is minus 8x minus 2y, and put the value. So that gives you what is called a differential equation. All of you know a bit about differential equation, right? This gives you x prime, compare the components, x prime t is equal to minus 8 and alpha y prime t is equal to minus 2y. From here you can eliminate alpha and have an equation in dy by dx. So that gives you that the curve, if you represent it as y equal to function of x, then it should satisfy this, and you can find a function which satisfies these properties, right? So dy by dx is equal to y by 4x, and the equation comes out to be x is equal to ky to the power 4, a solution of that. And k you can find because there are many curves along with the maximum, but you want the one which passes through the point, that is a given point. So put that initial condition, right? So that condition was at 2, 1, you put this passes through the point 2, 1, so when you put the value k is equal to 2, and that gives you the required path which is passing through this point 2, 1 on that surface, right, with that temperature will be maximum along this curve. So this is some kind of indicating that there are applications of these simple interpretations of directional derivative is dot product of gradient with the unit vector. The basic idea is of maximum increase is that of the gradient vector, the maximum decrease, right, is that of the negative of the gradient vector, and no change is the ones which are perpendicular to the gradient vector. And this idea we are going to use also to define, if you recall, we said we want to define the notion of tangent and normals to surfaces, right? So this is going to be useful there also. So let us look at a simple result which will help us to define the notion of, see, given a surface, you want to define at a point what should be called as a tangent plane to that surface at that point. And as I said, to know a plane, it is enough to know a normal to the plane at that point. If you know a unit normal vector, then you know the equation of the plane, because you know a point through at which it is passing through and a normal vector to that thing, right? And to find a normal to the surface, so the question is what should be called as a normal to a surface, right? A surface and a pointed thing, which one should be called as a normal? So the idea is we go to something called a lower dimension, in the sense that look at a curve on the surface. Look at any curve on that surface passing through that point. Now that curve has got a tangent vector at that point at which you are considering, right? At that point, you know what is going to be a normal to that curve. And supposing for every curve on the surface, you get a same vector to be the normal. Getting the idea? You are given a surface, take any curve on the surface which is lying on the surface passing through that point. So at that point, there is a tangent to the curve. So there is a normal, well-defined normal. So for every curve, there is a normal. Supposing it happens that all these normals coincide, they become one. Then you would naturally to call that as the normal to the surface. Right? So that is the basic idea. So we try to show that the gradient vector is the vector which is perpendicular to every curve on the surface passing through that point. So the gradient vector becomes the normal to the tangent plane which we want to define. So that is the basic idea. So let us, S is a surface which is given by implicitly by some equation fx yz is equal to 0, and on that you take any curve passing through that point P. So let us P is a point and C is a curve which is passing through this point P, and we want to show that the gradient vector, gradient is to the surface, right? It is related to the equation of the surface. That is perpendicular to every tangent. So at this point to the curve there is a tangent, and we say, we'll show that the gradient is, so take any other curve, say take any other curve, and there will be a tangent here, and will then still the same gradient is a normal to it, is perpendicular. So that will intuitively tell us that this we can call as the normal to the tangent plane. So the claim is that given any curve, okay, and the curve is given by some equation, so let us say that t is the tangent vector to the curve, then the gradient dot t is equal to 0. That will prove where t is the tangent to the curve C at the point P. So that is what we want to prove, right? And how do we prove it? So let us take an equation for the curve, say RT or gamma t, whatever you want to call it. Now that curve lies on the surface. So what is the meaning of that the curve lies on the surface? Equation of the curve is going to satisfy the equation of the surface, and that is given by fx yz is equal to 0. So, and equation of a curve is one parameter only, t going to xt comma yt comma zt. So we'll get f of xt comma yt comma zt equal to 0 for every t, and is at t equal to say 0 or t0 is passing through the point P, so it is going to be differentiable at that point, and then by chain rule we'll get the derivative, and that is what this equation is. So let us write down that proof. So C is having a parameterization gamma t, say xt yt zt, t between alpha and beta, and at the point t0, at the time t0, the curve is passing through that point P. So it's a curve which is a function of one variable t. At time t is equal to t0, it passes through the point P. And now this curve lies on the surface, so we must have that relation that f of xt yt zt is equal to 0 for alpha beta, right? And if f is nice, right, if f is differentiable, then chain rule is applicable. So we assume our curve is smooth, right? That means at every point it is derivative exists. So by chain rule you can differentiate with respect to t and get that gamma prime t0 Okay, that is the tangent to the vector, and let us assume that tangent is not 0. Okay, otherwise we will have naturally problems. So at every point there is a tangent vector which is not 0, and then the composite function f of xt, yt, zt, that is equal to 0. Apply chain rule, so you get g prime at t0 equal to 0. So by chain rule fx into x prime fy fy prime plus fz into z prime is equal to 0, and this is nothing but our dot product, the gradient vector fx fy fz dot product x prime t0 y prime t0 z prime t0 equal to 0. That is the equation of dot product. So the gradient at p dot t is equal to 0, where t is the vector x prime t0 y prime 0 at 0, right? So that is equal to 0. So that proves our result. So what we are saying is, geometrically, if you take any curve on the surface with the appropriate conditions satisfied, then the gradient vector to that surface, right? Surface is given by fx, yz is equal to 0. The gradient vector determined by that surface is normal to every curve on the surface at that point. So we'll call this as the normal vector to the surface. And once you have defined a normal vector to the surface, a plane, right, to which this is a normal at that point is called the tangent vector. So you can write down the equations of tangent vector and normal vector. So S is the surface, fx, yz is equal to 0. So it is assume it is a differentiable function, and of course we assume the gradient vector is not 0, normal vector is not 0. Then we can define the normal, this is called the normal to the surface at that point. Okay. And once you have the normal, you can define the tangent plane, that is a plane passing through that point ABC with this as the normal. So the equation is, of course, that is equal to 0. What is the equation of the plane with a normal and a point? That vector dot product with that is equal to 0. A dot u is equal to 0. So gradient to x minus a, x minus b, right? The point is ABC. Okay, a general point on the plane, that vector is going to be x minus a, x minus b, and x minus c components. So any vector in that plane is orthogonal to the normal. So that is what we have written here, that's all. That is the equation of the plane. So x minus a, y minus b, z minus c is an arbitrary point on the plane, and the plane is passing through the point ABC, that's why it is an arbitrary point. And gradient vector is 0 dot, that arbitrary vector is 0 on the plane. So that is the equation of the plane. Okay. You can write the line normal line, instead of writing the vector, you can write the line passing through, along that vector passing through that point as called as the normal line, if you want to call, right? You can write the equation of the normal line. So x is equal to a plus fx t, y equal to, right? That is the equation of the parametric form of the line passing through the point ABC, which is along the gradient vector. That is, you can call that as a normal line if you like. So all these things can be defined. But the basic idea is, so if these are, none of them is 0, then you can eliminate the variable t and write in this form also, right? Those are equations in 3 dimension. You are familiar with that. So the basic idea, as I said, is that the gradient vector gives you a vector which is normal to the surface. That is the important thing. And all other things follow nicely from the geometric considerations. So examples, so you don't have to do anything except we have to compute. Computation is simple, you have to compute only the gradient vector, right? Fx, Fy, Fz, and check that it is not 0, and then write down. So for example, let us write the special case when the surface is given by z is equal to fxy, right? Earlier we wrote as fxyz is equal to 0. That was the implicit form of a, like x square plus y square plus z square is equal to 9 sphere, right? But you can write x, one of the variables is explicitly representable in terms of the other variable. Then, so for example, if z is representable in terms of x and y, so z is equal to fxy. But this explicit equation also can be interpreted as an implicit equation. Bring z on the other side, so there is only fxy minus z is equal to 0. So capital F is equal to small fxy minus z. So you can write that way. And now you can treat this as the implicit equation of the surface and apply your formula. So calculate fx. Only here in this case fz comes out to be minus 1, right, when it is given explicitly. So that is the only change. So accordingly write down your equations. So compute fx, fy and fz. So that is the surface, and write down. So the gradient vector is fx, fy, fz is minus 1 because it is given explicitly. That is the reason. And that is never going to be equal to 0. So that condition, the important thing is in this case this is automatically satisfied because the third component is -1. So you don't have to verify when it is given explicitly. So that is the important thing to realize here. And once that is given, you can write down the equation of the tangent plane and the normal line by putting that fz is equal to 1 in that thing. So that is the equations of the tangent and the normal. When the surface is given explicitly. Okay? Right. So some examples. Let us say z square is equal to 2x square plus 2y square plus 4 and so on. So this equation can be written implicitly. You can write it as fxyz is equal to, you can take it this side or that side, doesn't matter which way you take it. So 2x square plus 2y square minus z square plus 4 is equal to 0, right? And from there you will get the gradient vector. So calculate the gradient vector, that is the gradient vector 4x 4y minus 2z, and at any point you want to say at this point you compute those partial derivatives, that gives you the gradient vector, that is a normal vector. So equation of the normal at the point 1, 1, 2 you can write down, okay, the equation of the normal line, and similarly equation of the tangent plane you can write in that way, fx x minus a plus fy y minus b plus fz z minus c is equal to 0. So that is the equation of the plane. Let us make it slightly more interesting, this routine kind of problems, drill problems. Let us take a curve of intersection of two surfaces intersect. They will intersect in a curve, right? So we want to find a normal to that curve. And the curve is the intersection of the two surfaces. So one of them is, say, sphere, and the other is this plane, right? A sphere is cut by a plane, so you will get, okay, a curve. And that the important thing is that curve of intersection lies on both the surfaces. That is the important thing to observe. And if the curve lies on both the surfaces, then the gradient of both the surfaces are going to be normal to that curve, right? So how will you find? So what is the important thing to realize here? That is a normal to that curve, right, at that point, because that is part of that surface. It is also part of the other surface, so gradient of that also is normal to that, right? And if you want a vector which is normal to both of them, linear combination, but that will be in the same plane. That should be the cross product. A vector which is perpendicular to both, so that should be the cross product. So that is the idea. So once you have made your strategy, what you want to compute, so at this point, write f, write g, right? And something a tangent to through the line to the curve will be something which is normal to both the normals. So we want the tangent line to that. So that will be the cross product of these two gradient vectors, right? So that is the only thinking part in the problem. So now is only computation of this. So compute gradient f, gradient g, take the cross product. Everybody knows cross product of vectors? Yes, so let us not bother about it. So you can write it in the form of determinant I, j, k and compute, okay, and that comes out to be, okay. So that is a vector which is parallel to this. So you can write down the equation if you like, RT is equal to, equation of line, it is parallel to passing through a point a plus tu, right? So a plus t, u is the direction along which it is going to go. Here is another application of this directional derivative. See, what is directional derivative? In one variable, derivative gives you rate of change of the function, right, at that point. Now, in the directional derivative, it is the rate of change in a particular direction, right? So we can use this, and rate of change, if you are moving a nearby point, right, then along that line if you move, you can get an approximation for the value of the function in that direction, right? As the derivative, the tangent line gave you approximation for function of one variable. So derivative here into the increment will give you the rate of change, right, approximate change along that direction. So directional derivative can be used to get approximate changes in the direction. So for example, so near a point P in a given direction, you can try to use this. So let us, so f of P plus tu, u is the direction given to you, right? At a point P, you are moving in the direction of u. So at a nearby point, time t you have moved. So f of P plus tu is the point where you have reached. You started with the point f of P. So f of p plus tu minus f of p divided by the increment, right? That limit will give you the directional derivative. So we can take this as approximately the directional derivative, that dot u, right? Directional derivative, as the formula was given by gradient times the unit vector, right? That formula, the directional derivative for a function if f is differentiable, directional derivative is gradient dot u. So we can take that dot u into the increment, that is absolute value of t. So this is the absolute, you can think of this as approximate value for this thing, rate of change. Okay. So this is another idea which is useful sometimes, so you can compute these kind of things. So here is an example which is in the notes also anyway. So this is a function of 3 variables given. So look at the gradient for this, that is a gradient for this, x plus cos z, okay, partial derivatives. So at the point p, which is 2 minus 1 0, compute that gradient, that is 2 1 3. So now we can find, say at this point we want to find the approximate change in the value of the function. At this point p I want to move towards a point 0 1 2, and we want to know what is the approximate change that will come in the value of the function. Okay. So when you want to move from p to q, that is the direction, so you will compute vector along the direction, make it a unit vector, right? Because you need a unit vector for the formula to be applicable. Directional derivative is equal to gradient times the unit vector in that direction. So find the vector along, so that is p minus q divided by this, normalize it, so that is a unit vector, and you are moving by a distance 0.2 units, so that t is 0.2. So you can compute f of t plus u minus f at the point p is the gradient times u into the distance you are moving, that is 0.2, and you can compute that. So basically the idea is you should know the direction in which you want to move and how much you are moving, right, by how much distance you are moving, and that gives you the approximate change in the value of the function. Okay. Like function of one variable, we looked at if a function is differentiable in a neighborhood, derivative exists, supposing derivative exists everywhere in the neighborhood, then you can treat derivative as a function itself in that neighborhood, and you can ask what is the second derivative of the function or the third derivative and so on. For a function of several variables, similar things are possible. You have the notion of partial derivative with respect to one variable with respect to another. Supposing these partial derivatives exist everywhere in the domain, then they themselves are functions of two variables. So that is important, or three variables. That is the important thing to note. Each partial derivative itself is a scalar field if it exists in everywhere in the domain or wherever it exists. Right? So you can ask whether this as a function of two variables or three variables itself has partial derivatives or not. So we are looking at partial derivatives of partial derivatives. But supposing the function is of two variables, fx is the partial derivative with respect to x. It is a function of two variables, so you can ask whether it has derivative with respect to x and y. So each one will have as many partial derivatives possible as the number of variables. Right? So you can have fx, then ask whether it has partial derivative with respect to x and y. Similarly, you have function fy, partial derivative with respect to y, whether that has partial derivative with respect to x or y. Right? So all such things, they are called mixed partial derivatives for a function of several variables. So let us just write down and notations used for that. So f is a function defined in a neighborhood in an open ball, say at the point x0, y0, and suppose both, so we are looking at only function of two variables, three variables, similarly third variable will be added. So no more major change comes. Assume that both partial derivatives fx and fy exist in this open ball, everywhere in the open ball. Right? Then you can ask whether the function fx has a partial derivative with respect to x or with respect to y at the point x0 or x0, y0 or not. Right? So if they exist, then you say they are the mixed partial derivatives, and these are the notations used for that. So fxx, there are two notations used. With f, you write lower xx. That means you are differentiating twice. First find the partial derivative with respect to x, and then again find the partial derivative with respect to x. This is also written as, in that del notation, del square f, del x square. This square indicates the second partial derivative, and this indicates x is being differentiated twice. Right? This is also same as del by del x of del f del x. You first find the partial derivative with respect to x and then find partial derivative of that with respect to x again. Okay? But let us just look at this notation. When your x changes to y, f x y. Okay? So when you are writing below, you are going to read it from left to right. Keep that in mind. So this is f x y means first differentiate with respect to x, then differentiate with respect to y. But in the other notation, so it is partial derivative with respect to y of the partial derivative with respect to x. So for your first differentiating, the inner thing, right, with respect to x and then with respect to y. So in this notation, you are going from right to left. In this one, you are going from left to right. So that care you have always to take, right? Whichever notation you follow, you do your operations accordingly. If you are writing it below, then you are moving from left to right. If you are writing that notation, then you are moving right to left. Right? Always anyway in arithmetic we know the bracket has to be solved first. Right? We have been told that formula of arithmetic simplifications. So bracket is to be first one to be solved. So you solve this first, that means you first find this derivative and then find that derivative. So 4 partial derivatives for a function of 2 variable second order mixed partial derivatives are 4. fxx, fxy, fyy and fyx. Right? So these are the possible things. They are called second order. You can have third order and so on. Right? They are called higher order partial derivatives. Now let us why one should go into this kind of second order derivatives and third order derivatives. In one variable we knew that if more information about the function, second derivative, that gives information about analyzing local maxima, minima or concavity, convexity and so on. But here there is a need from physical considerations. Many of the physical phenomena, when you want to model it in mathematics, write down the equations of that phenomena, that comes out in terms of mixed partial derivatives or higher order partial derivatives. Some of them you may have already come across probably in a course in physics, but let me just give you, there is something called one-dimensional wave equation. That is partial derivative with respect to u. So u represents the temperature of a uniform rod at a position. You have a uniform rod, you are heating one end of that and the heat is spreading through the rod. At any point on the rod, right, x is the point at a distance x from the initial point where the heat source is there. At a point x, after some time t, right, you are noting down the temperature and that is a function of 2 variables u, x, t. And you want to know how is the heat spreading. You want to calculate that, right? You want a formula so that you can solve it. So it says that from physical considerations, how this equation comes, you should ask in physics probably. Okay, I can tell you now also, but I don't want to go into. Probably there will be a course in partial differential equations later on for you, where you will see that these equations will come up and you will see how these equations are derived or how these equations are solved. So that is called a course on partial differential equations, which will come in the second year for you. So, but the idea is, this is called a wave equation, and here you see the partial derivative of u with respect to x, second order, and partial with respect to first order are appearing. So this is one of the very important equations which represents many physical phenomena called the wave equation. This is called the heat equation. Heat is spread. This is not the wave equation, this is the heat spreading. Wave equation is when you throw a stone in the water, you see the waves going on. Right? How a particle in that liquid, at what position it is. So that is the wave equation. So that is another one. So many places this comes up. It is also, another one is called Laplace equation, that is given by this. I just want to show you some of them so that when next time when they come to you, and here is the final one which is called the wave equation, that has second order partial derivatives on both sides. That is the position of at a point at a distance x from the center where you are thrown, right? Look at a point at a distance x, at what height, because the particle starts going up and down because of the wave, at what height it is, okay? So that is wxt, the height of the wave at a distance x, and that is given by the wave equation. So there are some important equations, all of them are partial differential equations. And more often than not, any physical phenomena you want to model will give rise to not only one partial differential equation, but a system of partial differential equations actually, which you may have to solve to predict something. For example, the weather prediction, how do they predict weather, right? Monsoons, what time, which direction, and how much will be the cloud formation and all such things. They collect data and form equations. What is the direction of the wind? That is a fluid kind of thing, which fluid is flowing at a distance x from somewhere at time t. How does the particle will look like? How does the cloud will look like? And many other things are there. So I'm just trying to simplify and say things. So examples of mixed partial derivatives, be careful, like functions of several variables, be careful at what point you are differentiating, okay? And you should look at the definition, okay? Don't take the first order derivative and then put limit of that as something that goes to something. Don't make that kind of a mistake. So for this, the first order partial derivatives you can just compute, they are this. And these are all again differentiable functions of two variables. You can differentiate each one of them with respect to either variable. So mixed partial derivatives you can compute fxx, fyy, and of course you can compute the other one. Okay? And in this case the two come out to be same. But normally the two are not same. So that is the important thing in mixed partial derivatives. One was the notation. If you lower notation you are going left to right. If you are writing the del notation you are going right to left. And the second important thing is that normally these are called the mixed partial, right? fxy and fyx. If you differentiate first with respect to x and then with respect to y, that may not be equal to other way around, right? These two may not be always. In this case, they happen to be equal. Let us look at one example probably where they are not equal. So let us look at this function fxy given by this at not equal to 0, 0, and 0 you can take the value to be 0. So what are the you can compute partial derivative at 0. You have to compute it separately at 0, 0. And at other points by using your product tool. So compute fx and so at 0, these are the partial derivative at 0, y 0 and x 0, y 0. These are the derivatives. So now you can see this is the function, okay, at a point y 0. If I want to compute its derivative at 0, 0 with respect to the other variable, what will that will come out to be? And of this is y with respect to x I want to differentiate now. The two will not be same, right? So the mixed partial derivatives in this case are not equal. One is 1, other is minus 1, okay? So the question arises, is a bothersome thing, right? In higher order things we will be having third order mixed partial derivatives and you have to keep track whether they are equal or not. So can we find some condition which ensures that you don't have to bother about these kind of problems that the mixed partial derivatives are not equal? And the condition is, it goes once again on the continuity of the partial derivatives. And the theorem says, supposing f is such that all the partial derivatives that are going to come into picture to compute fxy, you are going to look at fx as well as fy. And they are going to be differentiable anyway to compute fxy, right? So it says that all the four mixed partial, the two first order derivatives fx, fy and the mixed partial derivatives fxy and fyx should exist and be continuous in a neighborhood of that point. Then the mixed partials will be equal. So the conclusion is then the two mixed partial derivatives will be equal. Okay. So normally in most of the theorems one assumes this kind of, that your function satisfies these properties and hence you will have the conclusions. Okay. And they are all to ensure that the mixed partial derivatives are equal. We will not prove this theorem because the proof requires a very technical thing. So we'll assume this result. But let us just go back to that previous example that the mixed partial derivatives were not equal. That means what? What conclusion we can draw from here? In view of the theorem, that means that the second order partial derivatives probably are not continuous at that point. That could have been the reason only, because if they were true, then by the theorem they should have been equal. So let us try to verify actually that is the case. Okay. So for xy not equal 0, 0, you can compute the partial derivatives. So this is a second order partial derivative fxy of that function. Okay. You have to apply again the product rule, right? First order and then you apply the product rule. And similarly compute the, for this at the limit as, okay. Now you want to compute at what point? 0, 0, right? At 0, 0 you want to say. So y0 is equal to 0 as a function of x. Take the limit of that as x0 goes to 0. That comes out 1 and the other one comes out as minus 1. Okay. So this limit, however, the value of the function is minus 1. So the function is not continuous. So look at the mixed order partial derivative fxy, right? At the point 0, y is 0. We want to analyze continuity of this. Okay, second order mixed partial derivative. So I am going along the line y is 0 equal to 0. I am moving along the x-axis. Okay, x0 goes to 0. There is one path for the function of two variables. Along that, if the limit exists and is equal to value of the function, then no problem. But if I have a path along which with function of two variables the limit exists and is not equal to the value of the function, then that function of two variables is not continuous. So that's what we are showing here. So for this fxy, put y0 equal to 0 and compute the limit as x0 goes to 0. So limit of this going to 0, 0 along the x-axis. That limit comes out to be 1, but the value we know is minus 1. So this is not continuous. So verification that actually that is getting violated. That condition is getting violated. So this is one way of, because they don't exist, so reducing something as second order partial derivatives, at least one of them should not be continuous. So here actually both are symmetric and both will not be. You can check that they are not. I think I don't want to go more into topic today, because the next topic is going to be local maxima and minima for functions of several variables. So let me not do anything more, but let me just revise what we have done till now for functions of two variables, so that you have some idea of what is in store. You already know that for mid-sem we have already said that whatever is covered up to tutorial sheet Wednesday, that is 6, all topics, that includes differentiability and directional derivative and the applications of that, right? Up to that topic, problems in that. So that is the syllabus for the, okay. And essentially for functions of several variables, we have been trying to do whatever we have done for function of one variable in a similar way, right? The first thing we started looking at as a function of two variables, how you can understand the function, right? So there is something called, for a function, you of course like function of one variable, you have a natural domain for the function, right? You are given a formula, you can ask what is the natural domain of the function, where the function will be defined. So all values x, y or x, y, z, where the given formula makes sense, will be the natural domain of the function. And then trying to understand a function of two variables, the first concept was level curves and contour lines, right? So what are level curves? Level curves are part of the domain, right? Level curves are part of the domain. So D is a domain, right? You look at all the points x and y where a particular value z is taken. Function is z is equal to fxy. So you fix z is equal to c, and look at all the points in the domain xy such that fxy is equal to c. So level curves are curves in the domain, right? At the bottom, you can keep that picture in the mind at the bottom. So they are curves. Those are the points where a particular height is taken, right? If you are given a level curve for z is equal to c, that means those are the points in the domain where a particular height is taken. It's like describing a mountain on a map. In Atlas, you might have seen in childhood, sometimes for fun, just I open Atlas now and then to locate points. But graph of a topography of a land is given, where it is high, where it is low, and all kind of things. So they just draw some kind of, right, curves. So this curve indicates the height is 500 meters above the sea level, or this is 200 meters. So various curves are drawn. Those are level curves. Then other way is, you look part of that surface itself, z is equal to constant, right? That means what? Z is equal to constant means that height, and you are cutting that surface at that height. You look at the plane, z is equal to c, that will cut the surface in a contour, right? So a contour line are the lines which are parts of the surface, parts of the graph, which are at a particular height, right? Contour is shape, right? The shape of the object at that particular height, how does it look like? So those are contour lines. So contour lines and level curves give you some idea about what the surface is, right? And then to do calculus on functions of two variables or three variables, in one variable we knew that you can do calculus once you have the notion of distance, right? Something coming close, something going far, so notion of distance. So in the real line absolute value in R2, that is the magnitude of vectors, right? Distance between 2 points to P and Q is the magnitude of the vector P minus Q, right? And that is the usual Euclidean distance also. x0, y0, x1, y1, so x0 minus x1 square plus y0 minus y1 square root, that is a natural distance. So with that notion of distance in plane or in R3, you can proceed ahead and define all the concepts that you have done for one variable. So first thing is, look at limits of sequences. So given a sequence in the plane or in R3, right, you want to know when is the sequence convergent to a point. Of course in R2 or R3 accordingly. So I say sequence Pn will converge to P, same definition. You look at the distance between them, that should go to 0. So distance is a number. Now magnitude is a non-negative number, right? And we know for a sequence of non-negative numbers or a sequence of real numbers, what is the meaning of saying a sequence goes to a value? So saying Pn goes to P is looking at the magnitude of Pn minus P, and that distance goes to 0. Then you say the sequence Pn goes to P. And the important thing was saying the sequence goes to P is same as saying the component sequences converge to corresponding components. This is an equivalent way of describing convergence of sequences for two variables, right? And of course, though, once you have the notion of convergence, you can easily prove that the limit is unique and all those things. And if an goes to A, Bn goes to B, sum of the limits is equal to, right? All those properties are valid here also, because basically they are limit concept. Okay, so and component wise there it is true, so you can use that also if you like. So if a sequence Pn goes to P and Q1 goes to Q, then Pn plus Q1 will go to P plus Q. Same ideas work there, no much problem is there. Then we came to the concept of limit of a function of two variables or three variables at a point, right? And the basic idea is same again. Either you can take, you want to analyze limit of a function at a point AB. So either you can take sequences in the plane going to AB and look at f of image of that sequence and see if all of them converge to the same value, then we'll say the function will have a limit. Or you can write in terms of epsilon delta definition. Given epsilon greater than 0, there is a delta, so that if you look at a neighborhood of that point, related neighborhood of that point, the neighborhood is a ball now, right? Related neighborhood is a ball, so open ball around that point without the center, that is a deleted open, because you don't want to bother about the value of the function at that point. That is not important for limit. So P at any point xy in that neighborhood, f of xy at any point minus L should be less than epsilon for every point in the delta neighborhood of this, right? Epsilon delta definition. Basically same. Close by a distance delta, one variable. You forget about one variable or two variable or any variable or anything. If this is close, given you want epsilon closeness, there is a notion of closeness here in the range, right? You want epsilon closeness there, and given any epsilon closeness, you should have a delta defined here neighborhood. So all points in delta neighborhood go to epsilon closeness. And you define appropriately closeness, that's all. That is the concept of limit. It has all the properties that limit functions have, right? Limit of the sum is equal to sum of the limits and all those properties. Then continuity of the functions of two variables. Once again, it is limit of the function is equal to value of the function at that point. Same as it will work in any place where notion of distance is there, right? Limit is defined, limit of continuity, notion of continuity is available, right? But here the important thing was to prove something is not continuous, or if the limit exists, the limit along every path should exist. That is the difference between one variable and two or three variables. In one variable only two paths were available, left and right. So you have the notion of left limit and the right limit. But in the plane there are many ways of approaching a point. Along any curve you can approach. And it says if the limit exists, then we proved that limit along every path will exist and it will be same. So to show that limit does not exist, it is enough to produce at least one path, like just we showed today, along which the limit does not exist, or there are at least two different paths along which limits exist and are different, then the limit will not exist. And even if the limit exists not equal to the value of the function is not continuous. So that is continuity. An important property about continuity, we said that it has that same property that if a function is defined on a close bounded interval, right, then the function is bounded and attains maxima and minima. Same property is true for functions of several variables. Only you have to define appropriately what is a closed bounded domain, right? In the plane or in R3, what is meaning of a closed bounded? We know for closeness we define what are called the limit points, okay, and what are called interior points. If every point of the domain is an interior point, then the domain is open. At every limit point, we also define what are called the boundary points, right? So if every boundary point is part of the set, then the set is closed. And we did not prove it, but open and closed are complements of each other. If a set is open, if and only if, we say we can prove that, one can prove that. It is not difficult to show also. A set is open if and only if its complement is a closed set. It's not a difficult thing. But we did not prove it, but sometimes if you like, you can use it to say prove that something is open or closed. One of them may be easier to verify. Okay. So that is properties of continuous functions on closed bounded domains, because that will be useful in analyzing maximum, minimum of functions of several variables when we do it after the mid-sem. Okay. Then came, of course, the next notion was how to analyze rate of change of a function of two variables. So we looked at partial derivatives, right? Partial derivatives, existence of partial derivatives need not imply, it has nothing to do with continuity of the function of two variables. That was an important thing to note, right? Partial derivative exists, but the function may not be continuous and so on, okay? And then we came to the notion of differentiability of functions, which is actually the strongest notion of rate of change for a function of two or three variables. And that indeed implied, actually that inbuilt in that was all the partial derivatives exist, right? And we should have that condition that increments in each direction you should be able to write as f of x plus h comma y plus k should be written as f of xy plus the increment h times fx plus k times fy plus error functions h times error function and k times an error function, which are functions of two variables again. And then we showed a way of checking whether something is differentiable or not by taking that and dividing by h square plus k square limit is equal to 0. Another way of checking something is differentiable. Differentiability implies continuity, and we gave a sufficient condition for differentiability that was called the increment theorem. Namely, if the partial derivatives exist at that point and in a neighborhood and are continuous at that point, continuity is important, then the function becomes differentiable at that point. So that was the increment theorem. And then finally, we came to, instead of looking at only partial derivatives, you can look at directional derivatives. Right? Instead of going only along x-axis or y-axis, you can go in along any direction. That is the notion of directional derivative. And then directional derivative is related to the gradient if the function is differentiable. Right? So that is what we have done till now, and that is the portion till mid-sem also, right? Excluding, of course, tangent normals probably. Okay? That is up to what we have done. So let us stop the lecture here today.